So we're just going to start with basic logic. And the most fundamental piece of logic is called a syllogism. And this is where you have a conclusion that will follow from generally two premises. So, for example, all men are mortal, first premise. Socrates is a man, and thus the conclusion is that Socrates is mortal. Now, this is obviously a very obvious statement, but this is one of the most fundamental things. When you get to start using this with math and numbers, you can draw most of your conclusions using this. There's also the law of the exclusive middle, which states that any statement is either true or false, no in between. And if your two premises are true, the conclusion must be true, with no question. And we also have propositional logic. This is where you have two statements, P and Q. And whenever P is true, Q is true. And you would say P implies Q with this arrow here. And so, for an example, if it is raining, I will wear a rain jacket. If the statement, it is raining, is true, then the statement, I'm wearing a rain jacket, will also be true. And we can make that truth table here. So, it so we can evaluate the statement P implies Q. So if P is true and Q is true, then it is true that P implies Q. If P is true and Q is false, then that implication is false. And it is a little strange when your P is false. In essence, the statement doesn't hold. So it is assumed that both of these are true. And then we have some other symbols that you should be familiar with. P and Q with that caret there. And P and Q is true if both P and Q are true. So P is true, Q is true, the statement is true, and the rest of these will be false. Similarly, we have P or Q, which is true if either P or Q is false. So this is true, this is true, true, false. And finally, that means not, so it's essentially just the inversion of P. So when P is true, not P is false. So that's your basic prepositional logic. And we also have, if we assume now that P implies Q, we have the contrapositive, which is not Q, implies not P. In essence, going back to the rain jacket example from before, if I'm not wearing a rain jacket, it is not raining. So this is called the contrapositive. The contrapositive is always logically equivalent to the initial statement. So if this implication is true, the contrapositive is always true. You also have the converse, which is Q implies P. This is not always true. And there's a named logical fallacy for this. If you assume the converse to be true incorrectly, that's called affirming the consequent. However, if it is the case that P implies Q and Q implies P, we can say P if and only if Q, which essentially means that the statements P and Q are logically equivalent. So, we are going to do now a direct proof using some of these. And the PF is this abbreviation for proof. We're going to prove that the sum of two odds is even. So, by essentially the definition of odd, we can write any odd number n as being 2a plus 1, where k is any number. So essentially this is a general form to make an odd number. So let us have two odd numbers here for our proof. We'll have n, which is 2a plus 1, and m, which is 2b plus 2. So let's write out n plus n. This is equal to 2a plus 1 plus 2b. And then we can simplify this, 2a plus 2b plus 2. And we can factor out a 2. 2a plus b plus 1. Now, a plus b plus 1 is a integer, because we had assumed here that a and b are integers. So we can rewrite this a plus b plus 1 as any integer. We can call it k. So this is equal to 2k. And if you notice, any 2k will be even. If you're multiplying an integer by 2, it will be even. So regardless of your choice of n and m, if they are odd, their sum will always be even. And at the end of a proof, you'll see a couple of things to denote that the proof is over. Usually, you'll see a square. People will do 3 lines, or QED, which is a little dated, but it means quad arc demonstrandum, that which was to be demonstrated. You won't really see that too much, but maybe a bit. And we're also going to do a proof using the contrapuntal. So, we want to prove that if n squared is even, then n is even. And if we write this in the form of propositional logic, we can write this as n squared evens implies n even. Can anybody tell me what the contrapositive of this statement is? Remember, not Q implies not P.
N is odd implies n squared is odd.
Yes. So, now we want to show, for this proof, that if n is odd, that implies n squared is odd. So, by our same definition of odd, we are going to let n equal 2k plus 1. Therefore, our n squared is 2k plus 1. Splinter. And so we just simplify that a bit. Then we're going to factor a 2 out of just these terms. So, this 2. plus 1. And this should be a little reminiscent of our initial definition of an odd number. Because 2k squared plus 2k is also an integer, it's simply of the form 2a plus 1, which means that this 2a plus 1, which is our definition of odd, and we have our proofs. Because the contrapositive and the initial statement are always logically equivalent, proving this statement is the same as proving that if n squared is even, n is even. Alright, so now we're going to talk a bit about contradiction.
Could I ask maybe I don't know if this is a naive question, why did you do the contrapositive here? Why not try direct statement?
So you can do a direct proof. It's just a little annoying to go from n squared to n because then you have to introduce square roots. And it's just to show that sometimes you can manipulate a statement a bit to prove an easier thing that's logically equivalent. So you don't necessarily have to. It's just an option that you have. So for contradictions, we do not allow logical contradictions in math. So a statement P cannot be both true and false.
Oh wait.
So, why is this? Well, let's assume that some statement P is true and false. So, then we can put it into an OR statement. We can say P or uniforms are real. Because P is true, we know that this whole OR statement must be true. But P is false. So for the OR statement to be true, which we have already determined, the second term must be true. So essentially, if you accept a contradiction, you can lead to any conclusion that you want. This is called expulso quod libet, or from falsity follows anything. And it's really just a fancy way of saying, if that's true, anything could be true. But that is the reason we don't allow contradictions. It's also called the principle of explosion, because the logical conclusions you can draw like explode outwards. So we're going to do a proof by contradiction, which is a very useful tool. Essentially, you can assume the opposite of what you want to prove, lead it to a logical contradiction, and therefore that initial assumption must be false. This is called reductio ad absurdum, reduction to absurdity. So we're going to do this to prove that the square root of 2 is a rational setup. We're going to assume the opposite of this. Assume the square root of 2 is some rational number. So root 2 is a over b, where a and b are co-prime. Essentially, that this fraction is in simplest form. So, we can square both sides of this equation. 2 is a squared over b squared, and multiplying both sides by b squared. 2b squared a squared. So, this implies that a squared is even. So, we can then because a squared is even, by our prior proofs, we know that a must be some even number. So we can substitute it as 2k for some k. So, 2b squared equals 2k, 3 squared. And then we can simplify this to equals x squared, and dividing both sides by 2, we get b squared equals 2k squared. This implies now that b is even. So we have just found that a and b are both even, which contradicts our initial assumption that A over B is in simplest form. So in essence, there is no simplest form of this fraction. We have been led to a logical contradiction, so we know that this must be false, and thus root 2 is irrational. So, we have one last proof technique to discuss. Is everybody okay with me erasing this? And there's pizza in the back. Yes. Big piece. Yeah. And if anybody has any questions in the meantime.
That's it. On that work. That's it. That cool.
Oh yes, co-prime. It's essentially just to say that A over B is still simplest form. If everybody has their food and everything, we're gonna get started on proof by induction.
My card is good.
So it's a little bit of a strange concept at first, but the outline is you prove your statement holds for 1, and then assume some random n. If it holds for n plus 1, you know it holds for all natural numbers. We're going to work through it right now. So we want to prove that 1, let's take so on, up to n is equal to n times n plus 1 over 2. I'm sure a lot of you are familiar with that sum. So our base case is when n equals 1. This is pretty straightforward. 1 times 1 plus 1 over 2. So equal to 2, no, over 2, which equals 1. That's it. So now we're going to assume for some k that 1 plus 2 and so on up to k is equal to k times a plus m over 2. Now we want to prove that for k plus 1. So we need to show NTS is a common abbreviation you'll find for need to show. So we need to show that 1 plus 2 equals so on. No, okay. 1 to equal and k plus 1 values over 2. So we can already state that it's equal to the sum up to k plus k plus 1. So we're going to substitute that sum for k. So we have k times k plus 1 over 2 plus k plus 1. And we're going to get a common denominator here. So that over here is combine these fractions. And that reads that this is plus 1 times n plus 2 over 2. And that simplifies to 3 plus 1. Think that was close to that. So that's a little crowded, but essentially we just go through the algebra of adding this, and we end with the final solution that the sum up to k plus 1 is k plus 1 times k plus 1 plus 1 over 2. And so we prove that it holds for 1, and for any k, it holds for k plus 1. So from that we can deduce that it holds for 2, 3, 4, and so on. So it holds for all natural numbers. So we're going to start on some set theory. With the definition of a set. So, a set is a collection of any objects whatsoever, and it's denoted with curly braces. So, you have the set containing 1, 2, 3, the set containing letters A, B, C, literally anything can be an element of a set, and they don't all have to be the same. You could have 1, A, 3, it doesn't matter. Any objects. If you want to denote that something is an element of a set, for example, let's call this set S. We know that 1 is in this set, so we would write 1 is an element of S with that kind of epsilon symbol like that. So, subsets. Let's assume some set A is 1, 2, 3, 4, 5, 6. And we want B to be the set that contains 1, 3, 5. Because all of the elements of B are in A, we would say that B is a subset of M. So we would denote this as a subset of A. So, if A is a subset of B, let's actually change that in here. But so, if C is a subset of D, and D is a subset of C, that means that all elements in C are in D, and all elements of D are in C. So, C is equal to D. And this is called the axiom of extensionality. That's one of the main axioms of set theory, which is underneath all of mathematics. You also have a proper subset. So here with A and B are not equal. So sometimes you'll see people write where B is a subset not equal to A, or just with the subset with no line under moves. Sometimes you'll see people use this to mean any subset, which can be a little confusing notation. So, in general, stick to, for proper subset, putting slash below. Alright, so set building notation. If sometimes it's a little much to just write out every single element of a set. So, you can write out this set. So, you could write out the set of all x such that x is even. And this will be the set of all even numbers. It's just a short form way of writing sets. And you can also do set of x such that x squared equals 25. And this would just be equal to the set containing -5 and 5. So you can put any terms into those sets, really. One rule is that you cannot have a set of all sets. That leads to a lot of logical contradictions, so you avoid set of all sets. And we have some common sets that are used. You'll see this R with an extra line. Those are the real numbers. You'll see a Q, or the rationals, just Q for quotient. You have the Z, which is your integers, which is German for Zahlen. And then you'll have N, which are your natural numbers. There's a bit of a debate over if 0 is included in the natural numbers. It depends on the class you're in. If you're taking a set theory class, 0 will be included because I'm about to define what the natural numbers are, and it is built up from 0. And you also have the empty set, which has no elements. And that is what we're going to build all of the natural numbers up. Is everybody good with me erasing this group here? I also have a PDF of lecture notes that I'll send out afterwards, and I also have the text file for it, so if any of you are just starting to learn late, that you can go through and get all that. So first we're going to talk about some set intersections. We're just going to draw some Venn diagrams here. So if you want to denote the intersection of A and B, this is all of the elements that are in both A and B. And we can draw out a little Venn diagram here. So it's A, B, right in there is L intersection space. And you also have the union. A union B is all of the elements that are in either A or B. So, and B, A union B is that would be everything. So, those are just some symbols that you should be familiar with. We're not going to be doing too much with that today. Our natural numbers, we're going to define with the von Neumann ordinals. But so we start with 0 being equal to the empty set, no elements. And we let 1 be the set that contains 0, or that is the set contained or the empty set. And then we let 2 be the set containing 0 and 1, which is the set containing the empty set and the set containing it. So for any 10, it's equal to n union set contained, or this S, this is successor. So the successor of n is equal to n union with the set containing. We see here with 2 being the successor of 1, so 2 is equal to 1 union the set containing 1. And you build that up for all of your natural numbers. Now we're going to talk a bit about cardinality, which is a measure of the size of a set. Thank you. Let's see what that's good. So we'll denote cardinality. Let's let A equal the set. We denote cardinality with the absolute value lines, and the cardinality of A, because it has 3 elements, is 3. if two sets have the same cardinality or the same number of elements, you can call them the same size. And in essence, what that means is if we have some other set, B, A, B, C, that there is a bijective function between the two of them. So you have a function from A to B, and you could just map 1 to A to B, and 3 to C. And there's your function. It's a direct mapping. So this is very straightforward, but once we start working with infinite sets, it's a little more interesting. If we take the natural numbers, 0, 1, 2, so on, and we want to make it mapping to just the even numbers, well, 0, still comes, like, so you have a one-to-one mapping of these numbers. And so the cardinality of the natural numbers is the same as the cardinality of the even numbers, which is interesting because the even numbers are a proper subset of the naturals. If you remember from our definition of a proper subset, a definition of an infinite set, which will be called Dedekind infinite, is if it is equinumerous to a proper subset of itself. So the natural numbers are an infinite set because it is equinumerous to a proper subset of itself. So this also goes for the odd numbers. And interestingly, the integers are also the same cardinality. And we'll define countably infinite as anything which is the same cardinality as the natural numbers. The natural numbers are the smallest infinite cardinality, and we'll put cardinality of the natural numbers is equal to aleph null. So it is the smallest infinite cardinality. And you also have the cardinality of the even numbers is equal to aleph null. And we're going to show that the cardinality of the integers is also equal to aleph null. So if you want to visually do this, we kind of have a 0, we have 1, 1. And we have the whole line of integers here, and we want to enumerate them using the natural numbers. So we can start here and name this point 0. It's 1, 2, 3, 4, and so on. So we bounce back and forth. And does everybody see how every integer will be hit with this bouncing back and forth? And that every integer planned that, we just enumerate it. So that's your one-to-one bijection between the integers and the natural numbers. So the cardinality of your integers is also equal to aleph null. So we're going to define a Cartesian product. For some sets A and B, that's A, 1, 3, X, A, the Cartesian product of A and B cross B is going to be all ordered pairs of points that you can make from these. So some examples would be 1, A, 2, C, 3, A, etc. The order of these does matter. So A, 1 is not in this Cartesian product, but it would be in the Cartesian product with B cross A. So it is a fact that the Cartesian product of a countably infinite set, that being has the same cardinality as the natural numbers, is also countably infinite. So we're going to show that Z cross Z is also countably. So, Z cross Z is your ordered pairs of integers. So, for example, 1, 0, -3, 7, whatever. So, we can draw this out in a coordinate plane. And we are going to start iteration here with the 0. And what we're going to do is just snake around with 46. And at every one of these points, you're going to label 1, 2, 3, 4, 5, 6, so on, all around. And so we have just numbered all of the points, and if you keep going with this, you will hit every point in Z cross Z. So we have a bijection between the natural numbers and the Cartesian product. So these are also countably infinite. And I'd like to give a note on power sets. So if we have some set A, 1, 2, 3, the power set of A is the set of all subsets. So in this set we'll have just 1. The set containing 1 is a valid subset of A. You'll have the set containing 2, the set containing 3. You'll also have the empty set, because the empty set is a valid subset of any set. There's nothing in it, so it's in every set. You'll also have 1 and 2, 1 and 3, 2 and 3, and the whole set itself, 1, 2, 3. So, if I got everything here, there should be 8. So, the cardinality of the power set of A is always equal to 2 to the cardinality of A. Cardinality A is 3, so this cardinality is 8. And it is always true that the cardinality of a power set is larger than the cardinality of the set. This also applies for infinite sets. That and we want to prove that the real numbers are not countably indifferent. because, and there is a very likely proof of it, that the real numbers are the power set of the natural numbers, which intuitively, if you had some string of decimals, you can take subsets and write it out. However, it's a bit of a long proof. But the real numbers. Let's say we try to list out every real number. So we're going to enumerate them as we have been doing. Then we can debate. Just an arbitrary irrational numbers here. So, and let's say we did list out every single real number. We can then construct a real number that is not in this. So, in the 0th position of this number here, which we'll define as before the decimal place, we're just going to change that. So, make it a 7. In the first decimal place here, we're going to change that. Make that an 8. 2. In the second decimal place, we would change that. Third decimal place.
7.
4. Fourth decimal place, give that any number really. Doesn't matter. So, we would go down the whole list here and just change that digit in its respective place. So, this number is not in our list. Why? Because if you think it is somewhere, say in the 32nd spot, well, the 32nd decimal place is different in the 32nd spot. It's different in the second decimal place from the second. And so, with all of the numbers on this list, this one is not in here. So, no matter what listing of real numbers that you do, you can never break that them all. You'll always have at least one that's missing. This is called Cantor's diagonalization argument. And this is a proof that the cardinality of R is greater as their cardinality of natural numbers. So, does anybody think, well, so we know that the cardinality of your reals is larger than the cardinality of your natural numbers. Does anybody think that there's some set in between them?
Yeah, I do.
Does anybody else?
What can it be the cardinality of real numbers minus 1?
Well, the cardinality of real numbers minus 1 is the same cardinality. That's an odd product of from before where we saw the even numbers were equinumerous to the natural numbers. If you remove one element, that is a proper subset, but by our definition of infinite, it can be equinumerous to a proper subset of itself. So, what's the rational? The rational numbers are equinumerous to the natural numbers. If we go back here, we can set these ordered pairs as, well, that's the point 1, 1. This is the point. Yeah. 2, 3. and just say that this point is 2/3, and this point is 1/3, and this point is minus 2/3 over here. So just by using this kind of grid layout, you can make a formula for all of the rational numbers, and it's the same method. So actually, it is impossible to prove whether or not there is a cardinality in between them. But we do know that the cardinality of the reals is the cardinality of the power set of the natural numbers. However, that goes to something called Gödel's incompleteness theorem. Which says that in any system of axioms, and we encountered some of the axioms today, like the axiom of extensionality, where if two sets have the same elements, then they're the same set. There's a lot of these axioms. There's an axiom of infinity. There's the axiom of choice, which lets you have things like induction. So there's a lot of these axioms. But in any system of axioms, there will always be statements that cannot be proven true or false. So depending on the field of math you're working in, some people will assume that there is a set between them. Some people will assume that there's not. It's not something that within these axioms of set theory, which are the main axioms for any field of math you'll be working in for the most part, it's impossible to prove this thing, which is a little disappointing, especially because before I had given the law of the excluded middle, there are no statements that are both true and false. So it is either true or false. We just can never know pretty much. And that's, I think, enough for today. That was a lot of information at once, kind of a big slam there, but it'll be a good preparation for any future events we do. You'll have a knowledge of the symbols, some of the logic behind it. If anybody has any questions.
I'm just wondering, when we're like comparing things like cardinality at different like sensitive numbers, like the naturals or the integers or the reals, are there any sort of like maybe applications of physics or any other like applications outside of math in which that knowing stuff about that can be true?
I'm not entirely sure. I am a pure math major. I'm trying to think if there's anything off the top of my head. I know, actually, you'll be working a bit with, if you're doing any kind of like quantum mechanics and things, there's some group theory involved there, which is you have a set and an action you can perform on that set, and your set would be your basis of the quantum state or whatever, and actions would be some rotations of that, etc. And then the sizes of those quantum states, you can have infinitely long series of that, then it would be applicable. I don't know exactly off the top of my head an example, but question. All right.